Hello everyone, in this video we're going to be talking about how to make alcohols by using organometallics compounds. The most common organometallics are going to be the organolithium and the organomagnesium compounds. The organomagnesium compounds are also called the Grignard reagents. What's so good about these compounds is they have a very polar bond between the carbon and the metal, or you can also say it's an ionic bond technically because it's a metal and non-metal bond. So if I focus on just in generic terms, I have a carbon magnesium bond, and I can probably just gonna have write down CH3 there. You can have anything in the form of your alkyl group, and then you usually have some halogen there. I'm gonna write down X there. So this carbon and magnesium bond is polar, where I can have a full negative charge on the carbon and a full positive charge on the magnesium. So one way of writing those would be just having, a partial negative charge here, partial positive charge here, if you're showing the bond in there, but you can certainly write this in this form as well, where I can go ahead and have a full negative charge on the carbon and a full positive charge on the magnesium. So this carbon having a full negative charge is going to be acting as a strong base and a strong nucleophile. And the same story goes with the carbon and lithium bond. When I'm looking at this carbon lithium, we have a very similar situation where the lithium is a metal, carbon is a non-metal, so you're going to have a negative charge on the carbon with a lone pair and a positive charge on the lithium. Now, if someone asks you, okay, between those two, who is more ionic, or you can say who is more polar bond? Well, obviously lithium is less electronegative than the magnesium because it's a little bit on the top and it's on the first group. So lithium carbon bond is more polar than a carbon magnesium bond, and as a result the organolithiums are a little bit more reactive than the Grignard reagents, but for a sophomore organic course, more or less they do the same results. So they have very similar results when it comes to doing those reactions. So that's why I have put those together. So what you need to know along with that about these compounds, that they are strong bases and strong nucleophile. So you want to avoid using any protic solvents. So protic solvents would be something like water or methanol, or even acetic acid, because these guys, being strong nucleophiles, are also strong bases. So if you have these product solvents, they actually going to be doing these acid-base reactions instead of a nucleophilic electrophilic reactions. And as soon as they do an acid-base reaction, it's actually going to kill this um, nucleophile. So that's just a useless thing to do. So that's why you want to make sure you avoid using these protic solvents. However, you're going to be working up with an acid or water with an methanol at the end of these reactions, but that's being added after the reaction is usually completed. Now let's talk about how you actually really make those. So I'm just going to briefly talk about the mechanism, how you're really going to be making these Grignards and organolithium. They are very simple. They goes with this non-chain radical mechanism, where I know magnesium has two valence electrons. So I'm going to go ahead and break this carbon-bromine bond homolytically. And when I break this homolytically, it means one electron goes on the carbon, one electron goes on the bromine. So I'm going to go ahead and take one of the electrons from the magnesium, and it's going to get combined with the bromine. So as a result, you make this. So I'm just going to go ahead and write this down. So you make this radical here. So I'm just copy this down here so that we can have the color combination here. So I got a radical here, and then I got a magnesium and with Br, but then remember you still have another radical there, and then you can go ahead and combine that again. So this gets combined again, and then you end up making this Grignard reagent there. So I'm just copy this down here, and then I can go ahead and create a new bond here, and then MgBr. And remember, this carbon magnesium bond is going to be polar, so you can either write it this way in the form of the bond. So I can also write this down in this form, where I'll say, okay, I got a negative charge on this carbon, and then I have MgBr here with the magnesium with the positive charge. So either way, it's fine. And the typical solvents you're going to be using to create these Grignards is going to be the ether, because ether is a polar solvent, but it's an aprotic solvent. So polar solvents are needed for better solvation because you're creating the ions there. So if you have a polar solvent, it will create a solvation layer there. But you want to make sure you don't use anything that's protic solvent. So a very similar story with these organo lithium. In case of organo lithium, you're going to be needing 2 moles of lithium because lithium has only 1 valence electron. In case of magnesium, you have 2 valence electrons, and 1 magnesium was good enough. But here you're going to be needing 2 lithiums. Mechanism is still going to be more or less very similar to one another. So you kind of break this, create kind of radical there, and then you make in the first step, I'm just going to go ahead and copy this down. So I'm going to have radical there, and I have created LiBr here. And then remember, you got the second lithium there, and that second lithium electron is going to be getting combined with this radical here that you have created, and that would make this organolithium compound. And I can go ahead, I'm just going to go draw the bond right there. I can draw a bond right there, or even I can go ahead and write it like this, where I just copy this down. I don't have to draw the bond, and I can just say, all right, it's got a negative charge there, and I got Li positive there. So when it comes to these Grignards and organolithiums, they're not only limited to alkyl halides. They can go with allylic halides. They can go with these aromatic halides. They can go with these cyclic halides as well. So, and even vinyl halides. So I'll have different examples as we move along so that you can see different types of Grignards that are being used here. So once you have created these Grignards, and this is going to be the first way of, this is going to be the way of creating the Grignards or the organolithium, you can react with those different compounds that has the carbonyls, especially, for example, aldehydes, ketones, acid halides, anhydrides, and esters, and they can make alcohols. So I'm going to talk one by one with starting with the aldehyde. So if I have a formaldehyde, like in this case, what I know about this aldehyde or any carbonyls rather is carbonyls are polar, where you got a partial positive charge at the carbon and a partial negative charge at the oxygen. So I know I'm using this Grignard, and in this particular case, at the Grignard I have is a CH3 MgBr, and then someone might wonder how you actually make this in the beginning. Well, I can use methyl bromide, and I can use magnesium in the presence of ether, and that will end up making CH3MgBr. Okay, so um, once you have created this Grignard, I can go ahead and have this CH3 minus, because I know this is going to be a negative charge on that carbon because of this polar bond, and I can go ahead and have this attacking right there, and this comes out, and that's going to be the mechanism for this one. So it's not that complicated, relatively simple mechanism. So I'm just going to copy this down, and I'll take these things out for a minute. So you still have an oxygen there with a negative charge. So you do create a new bond here. I'm just going to draw like this, and remember there is a CH3 group on that bond there. I don't really have to write down the CH3 group, but if you want to go ahead and write down the CH3 group, that's completely okay, and I can go ahead and do the color combination there. So CH3 is coming from the Grignard here, and then in the second step, all you really got to do is just protonate this thing again. And when it comes to protonating these reactions, as a matter of fact, any Grignard or organometallic reaction is going to be worked up in the presence of water and or a dilute acid. So either one of them is fine here. So I can have, suppose I got this dilute acid here, or even water is fine. I can go ahead and protonate that. And then this comes out like this. And then you end up making this primary alcohol. Okay, so if you're using a formaldehyde, so if the reactions with aldehydes, if you're using formaldehyde in any Grignard reagent or organolithium, you end up making a primary alcohol. But and its primary alcohol is not really chiral, so you don't really have to worry about the stereochemistry. And if this was actually chiral, then you would have to worry about the stereochemistry. Now let me take an example where you actually have to worry about the stereochemistry. Now the second example is still using an aldehyde, but it's not in a formaldehyde. So the Grignard I have here is the phenyl group, which technically is going to look like this. So you could see something like that, or you may see in the books written something like that, because remember the phenyl, the abbreviation is the pH. So I can have this doing the attack right there, and it's breaking up the pi bond. And now in this particular case, I'm about to make a chiral center. So since I'm about to make a chiral center, you gotta worry about, I can have this phenyl attacking the carbonyl carbon either out of the page or back into the page. So I have two possibilities, each being a 50%. So you will end up making a racemic mixtures in this particular case. So I'm just gonna go ahead and just copy this down so that I can keep the color combination there. So I could have this phenyl coming out of the page like this, and I'm just gonna write down the phenyl, the pH with that, or you can even draw the structure if you want, but I'm just gonna write down the pH there. So it could be either coming out of the page, and obviously I'm gonna have the lone pairs on the oxygen now with a negative charge. And then in the second step, we can protonate that with water or dilute acid. So in this case, I'm just using water, and you will see only water used in some of these reactions, which is completely okay, because you can have these alcohols and waters. Alcohols are a little bit more basic than water, so you could have this reaction actually going even in the presence of water, but still an acid-base reaction at the end of the day. It's not really anything fancy here. So I'll get this OH here. And then this was done if you have this phenyl group attacking coming out of the page, but then you can also have the phenyl group attacking back into the page. And if that's the case, we could have another stereoisomer of that where the phenyl is actually going to be going back into the page. So you make a pair of enantiomers in this particular case. Now you really have to worry about this chirality only if there is a chiral center. And if there's no chiral center, you don't really have to worry about the stereochemistry and all that. Okay, what about something like this? We got the reaction with ketone. Okay, before we go down there, actually, I still want to talk about what type of alcohols you just made. If you see, we had a aldehyde, and then upon doing one attack with the Grignards, we made this secondary alcohol. So you made a primary alcohol using the Grignards when you were using formaldehyde, but we made secondary with just a general aldehyde. But now, if we're doing in a ketone, you will end up making a tertiary alcohol. So the mechanism is going to be very similar. I'm not really going to draw it in this case. The only difference is you have this different type of Grignard reagent here. I got the vinyl halide here, a vinyl Grignard reagent. Now, how do you really make the vinyl Grignard reagent? You can have the vinyl halide, something like this, and I can do add magnesium in the presence of a dry ether here. When we say dry ether, means it needs to be away from the water or in the absence of water at all. And this is what you're going to make here. So I know this is going to be the negative charge, and I really got to do is just attack this, and this comes out here. And now again, this carbon is going to be the chiral center, and since it's going to be the chiral center, you could have this nucleophile, which in this case is the vinyl coming out of the page or going back into the page. So mechanistically, if I just draw it briefly, I'm just going to copy this down here. So I can have this oxygen going back into the page. And if that oxygen is going back into the page, I would have that vinyl will be coming out of the page. That's one possibility. And then you can protonate that with the acid or even with the water. Either way is fine. You usually use dilute acid. You don't really use a very strong acid in these cases when you're just trying to protonate the alcohol. So it's something you got to be careful with. So that's an OH there. And then obviously, like I said, you can have this vinyl either attacking from the left or from the right, or you can even say from the top or from the bottom. And in that case, you can have a pair of enantiomers, or another way of saying the racemic mixtures. The difference would be now in the second case, I would have the OH coming out of the page, and this would be going back into the page. So you can do the RNS on this particular one in that case. So when you're using this ketone, you actually end up making a tertiary alcohol. And it is indeed chiral in this particular case. What about if you use these organolithiums or, organo or the Grignards with the acid halides, esters, and even anhydrides? I forgot to write down the anhydride, but anhydrides also works the same in this particular case. Um, the difference between the reactions of acid halides, esters, and anhydrides, and with the reactions of aldehydes and ketones, is they actually go in there twice. And when this goes in there twice, you will have to use an excess of Grignard reagents or organometallics, or you have to use at least two equivalents. So you may see either reactions writing two equivalents, or you may see reactions writing that this is going to be an excess amount. So what really happens mechanistically? So let's talk about that. So still, the first step is very similar. You're going to have this reagent here, this organolithium in this particular case with a negative charge here, uh, doing the nucleophilic attack, and pi bond comes out. So in this particular case, you again make this tetrahedral intermediate. These tetrahedral intermediates are high energy intermediates, not very stable. Let's get a negative charge here, and then we make a new bond here. It's going to dry right there, and obviously you're going to have this guy attached to it. So I'm going to show that right there. Now, in case of in case of ketones and aldehydes, when you do this attack, this oxygen gets protonated and makes the alcohol because there's no good leaving groups. But when it comes down to acid halides, esters, and anhydrides, they actually have a leaving group where this lone pair from the oxygen, when it's in the tetrahedral intermediate, it comes back to recreate the pi bond, and it's going to kick out this X here. In this case, the X is going to be any halogen. It could be chlorine, bromine, or iodine. I'm just going to go ahead and write that down. The X could be chlorine, bromine, and it could be iodine as well. So when this comes out, you end up making, so I'm going to try to do the color combination there. So you create the double bond here, and then remember you have this right there, and I'm just going to copy this down. And this right there. So you end up making a ketone here, and then this ketone, just like we did earlier, would react. So this will react again, and let's see what that's going to make. So again, I'm going to go ahead and take this. And then this obviously is going to go attack again here. Pi bond breaks. And now you make this tetrahedral intermediate again. I'm just going to erase part of that. So with a negative charge there, so now you got another one here, and obviously you're going to have this cyclohexane type group here. That's our that's our organometallics here, and then eventually it gets protonated in the last step with acid and water. So this gets protonated, so you make a tertiary alcohol. Now the difference between the alcohol you make here and the alcohol you had made in the presence of with the ketone is this one is actually not going to be chiral. And the reason why it's not going to be chiral, because remember your Grignard or your organolithium here gets added twice, and since it gets added twice, you have two same groups. This group and this group are the same, so it's not never going to be the chiral. So that's how you know sometimes if you are actually making the tertiary alcohol from the ketone, or you making from either the ester, acid halide, or with the anhydrides, because in those cases you're going to have two R groups to be the same, but in case of ketones they may not be the same unless you already have one of the R groups in the ketone side chain to be the same as that of your Grignard reagent. So this is how you're going to be making the alcohols using the Grignard reagent with the help of these carbonyl compounds. And then the last thing I want to talk about is how would I really do this particular one. I'm not really going to talk about the mechanism here, but I got the Grignards and I got the ester here, and I'm going to do this, I'm going to add this twice, so make sure you have an excess here, or at least two equivalent, and at the end of the day the product would look like this. So we have an OH here, and then I got two groups there that are being added twice there, something like this. So this is how the theoretical product gonna look like in this particular case. You can also add these Grignards to the epoxides or oxyranes as well, and they can end up making the alcohols as well. So the thing about epoxide is there's a couple of things you have. You have a ring strain, so those rings are fairly reactive because it's a three-membered ring, and in addition to that, there is a polarity in the bond because there's a carbon-oxygen bond where this carbon is going to be partial negative, partial positive rather, oxygen is going to be partial negative, and the other carbon is also going to be partial positive because it's connected to the oxygen. Now if I call this carbon 1 and call this carbon 2, where would your Grignard or your organolithium R or your nucleophile here is going to attack? Now remember, this R minus here is a strong nucleophile, and since it's a strong nucleophile, it's going to look for the most readily available site, which is actually going to be the carbon 1, because your carbon 2 is actually hindered. So when this attacks on carbon 1, this is going to break open this epoxide ring, and you end up getting this particular compound here. So I'm going to try to do the color combination there. So I got, so keep in mind, I'm not really messing up with the stereochemistry of number 2. So you're still going to have this oxygen coming out of the page, so be careful with that. But then I have this new bond made. Now this terminal carbon, which is carbon number 1, is actually not really chiral, so I don't really have to worry too much about the stereochemistry. But it always does in a backside attack because it's kind of similar to like an SN2 type reaction. So you're going to have an R there, but I didn't really draw this pointed down because it's not a chiral center, so you don't really have to worry too much about it either. And then in the next step, I can go ahead and protonate this using water, or I can have a dilute acid doing that. So either one is fine. So this reaction is going to be in equilibrium because there's not much a difference in the pKa's of alcohols and water. So a lot of time you would actually add a little bit of acid just to kind of make sure that all the alcohols are all these oxygens are protonated and made the alcohol. So you're going to have an OH there. What about if I have something like this? So this is another epoxide. So now I got both of those carbons to be the chiral center. So I'm just gonna randomly call this 1, call this 2 here. Now this phenyl here with a negative charge, or I can also draw it like this with a negative charge. Where would that attack? Would that attack carbon number 1 or carbon number 2? And like I said, it's going to be attacking the most readily available carbon, which is actually going to be carbon 2. So this attacks right here, and this opens up the ring, and then you protonate that with water in the second step, or with the acid in the second step. So let me just go ahead and copy this down here. And also, I said earlier that it doesn't have backside attack, so that's another thing you got to be careful with. So you don't change the stereochemistry at carbon number 1, because that's not the one that's actually being attacked. So you leave those substituents on it as they appear before. But now when this Grignard attacked this carbon number 2, it's going to be attacking from the behind. So this guy is actually going to be going back into the page. So this is how it's going to look like. And you're gonna have this right there. So this is, and then you go ahead and protonate this in the next step. So in this case, I have written down the acid there, so you can use the acid to protonate that oxygen here. And then you end up making this final product that you have. So you end up making an alcohol again. So this is how you're going to be using metallic compounds, especially the Grignards and organolithiums, and you can also have sodium and some other metals in there, but lithium and magnesium are the most common ones, so that's why I've written those down, and you're going to be using different other compounds to make alcohols. If you have any questions, feel free to leave any comments in the section below.